Welcome back. So in this video, I'm going to be discussing a pet peeve of most Mechanics 1 students, which is how to actually calculate properly the sign of the work done by a force on an object. So technically, when we see an image like this, like the one I have on the screen right now with a mass and a force exerted on it, very quickly, students understand that they need to go the direction here of a dot product, which is going to involve the force and the displacement. And this can be opened up again over here in terms of a cosine of an angle. This angle phi is the angle between F and delta D right now. There is an integral form of this equation when we are not dealing with constant forces, but rather space-dependent forces, forces that change as you move along a certain direction. So this is a big no-no, though, for Mechanics 1, as integration is not really part of the curriculum. And sometimes it's not even necessary, and I would say overcomplicates things that we can get in much easier ways. Now, focusing on this equation right here, if one was to ask you, what direction right now is this box moving? I have not told you so, and therefore you can't calculate the work done. But if I start off with the example here by giving you this direction, right now you would notice that these two guys are actually parallel, and the angle they make together, since they're parallel, is 0. Therefore, what goes into this phi is 0, and cosine of 0 is simply 1. So you would be able to tell me that the work done by this force is F delta D, and it's positive. Flip this around right now and pretend that the box was heading right now in the left direction, and this force is decelerating this box. And we have right now, if we see these vectors to be anti-parallel, which means they make an angle of pi, and we know that cosine of pi is simply -1. Therefore, I have the same answer, but a negative sign. Of course, I could have the force itself right now be perpendicular to the actual box and its direction of motion, in which case, again, this angle here would have been pi over 2. And we know that cosine of pi over 2 is simply 0, so we wouldn't get any work done, as we know from forces that are acting perpendicular to the direction of motion of an object. But one more thing I haven't really talked about is, what if I did not give you right now where we're moving at all? So if I was actually just giving you this, what could you say about the work done? And the way you would deal with a problem like this would be to actually figure out the tendency of this object, which will eventually create displacement. So to find the tendency, if there were more than one force on it, I would actually just find the net force and see in which direction it acts, see what direction my box can move, therefore that will be the direction of the future displacement. In this case, it's very easy to determine the tendency because the only force is F and it's directed to the right, which means right now the actual tendency will be to the right as well, since this is the only force, and that means in the future the displacement of this box is going to be going to the right. Now, looking at this, we see that even if I didn't tell you where the box was moving, I'm able to deduce right now that the actual force F is going to do, it's going to do a positive work. So in this problem where we had no velocity in the beginning, we found the tendency, we actually found the displacement from that tendency in the future that we're going to have, and then we see that they're aligned. Therefore, that cosine term will produce a positive one, and we will get a work done F delta D. Very nice. So, moving away from a problem like this, another problem that you may encounter, we can add a little bit of a layer of a complexity here, where we have a mass, for example, that is climbing up an incline right now. And typically, you'll see this problem. They'll give you the amount that it has traversed along the hypotenuse here of the incline. It will be some value d. And they'll ask you, what is the work done by gravity? First thing you should be doing here is understanding where gravity is pointing right now. It's pointing again straight down toward the center of the Earth. We know that. And since I know that, I look at my displacement vector, which is this blue arrow, and it goes up and to the left. So it's neither aligned nor disaligned with mg. So what do I do to prove if the sign of the work is going to be positive or negative? Well, I simply break this d down into components. One component here is going to be perpendicular to the axis of mg, and the other one is going to be parallel. I see that for the component that is actually parallel, these two are anti-parallel right now. So I deduce that the sign of the work done by gravity will obviously have to be negative right now. Okay, so how do I find the size now? The size of the work done by gravity? Well, to do that right now, one could integrate, but we said we're not going to integrate. A more clever way is to just focus on the fact that gravity is a conservative force. And therefore, we can find the work it does through the change of the gravitational potential energy. And that's exactly what I'm going to do here. I'm only interested in the size of the change here. So that's why I'm including the absolute values, because I've already established the sign is going to be negative. So how can I write delta UG? Well, I know that UG is mgh. And I know that these two, mass, for example, doesn't change for my object sliding up the incline. We're assuming that we're near the surface of the Earth, so G also stays constant. And then H is the only one that actually changes, which is the height that you move, up the incline right now. So I can express the difference in the gravitational potentials as we can factor out the mg and write the difference of the heights instead over here. Now, putting in an arbitrary 0 on my diagram for the height, maybe here, I can see that in the beginning with the 0, it makes my height here equal to 0 in the beginning. Could have put that 0 anywhere on that diagram, by the way. I just choose to put it at the bottom. And then my height up there will have to be the length of this side of that triangle. Lucky us, we have this inclination angle, and we have the size of the hypotenuse being, again, just d. So that side right there is going to be nothing more than d sine theta, since it's an opposite to that angle. That means the height that I have in the end here is d sine theta. And moving on over here, we see that we just get, for the size of the work done by gravity, mg d sine theta. We can drop the absolute values right now because no theta here will actually produce a negative value. Theta can range from 0 to 90 degrees, so no negatives from sine. And these are all sizes, so they're not going to be negative. Now, putting it all together, I can very easily tell someone what the work done by gravity is. Its sign is going to be negative, and the size is going to be mg d sine theta. And problem solved, right? I don't have to worry about it anymore. So that's, again, given this set of variables, how you could go about describing this. But what if I instead, over here, I have the same exact problem, but I'm actually given velocities of my object. Like as it's climbing up the incline, I'm given different velocities for these positions of the box. Well, again, I know that the displacement of my motion is heading in this direction. I know that one of the components right now, the one along the axis of gravity, is anti-parallel right now, and the other one, of course, doesn't do anything over here. But these two are anti-parallel, which makes the sign, again, of the work done by gravity here, makes the sign negative. However, when I go and talk about the size now of the work done by gravity, I don't have any information on heights or distances traveled. So I'm going to do the next best thing. I know that the energy wasted over here by the box, the energy wasted from its kinetic state, it has all gone into increasing its gravitational potential. So I know, in other words, that the work done by gravity should be the change in this kinetic energy. And knowing that kinetic energy, again, can be written as mv squared over 2, the only thing that changes during the ascent is v. So I can write the change by factoring out the m over 2 because it doesn't change, and then comparing v final to v initial. Right here, right now, we have that in the v final, we have a velocity v2, and at v initial, we have a velocity v1. Okay, so we can pull the m over 2 outside the absolute value because, again, this cannot be negative. However, our velocities right now, the way we're doing the subtraction, v2 is bigger than v1. Therefore, the subtraction done in this direction will yield a negative that we don't want. We want the size, after all, which is positive. So we keep the absolute values here, unfortunately, in place. And combining right now the two things that we've determined, we can talk about the work done by gravity as negative m over 2 absolute value v2 squared minus v1 squared. Now, I know what you're thinking. You can probably write this without the absolute value, giving the same result overall. And yes, you can write this to give the same impression. You can write it as m over 2 v2 squared minus v1 squared, because you know that this quantity will be negative right now. So we'll account for this negative that is found outside the first expression. So these are equivalent. These are equivalent ways of writing this thing. So it's up to you how you want to write it, but this is the answer now about the work done by gravity. You see very different answers between this and the previous part, and yet they are exactly equivalent, but we're given a different set of variables on each scenario. We can extend this this concept to talk about springs, and springs over here, we'll start with an example where I've given you the stiffness, and I'm compressing right now the spring from its equilibrium position all the way to an amount delta x beyond the equilibrium. Now, if someone asks you, what is the work done onto the spring? Well, to determine that, I look at the spring, and I know right now that to compress it, there must have been a force acting in this direction right now. F spring, though, is space dependent, which would suggest integration. However, I said we're going to avoid that. Now, to compress the spring itself needs to move in this direction right now. This is the direction of delta D. So looking at these two, we see that they're aligned once again, and it means that the sign right now for the work done onto the spring is going to be positive. Makes sense. The spring gains energy, therefore the work done on it is going to be positive. Okay, so how do I find the work done? The size of it, I should say, of the work done on the spring. Okay, well, this one is fairly straightforward. I don't have to integrate right now F spring along the direction of compression. I can simply use the fact again that the spring force is conservative, and it is expressed in terms of a potential called the spring potential. So I can express this work done as the change in that spring potential. Spring potential itself being kx squared over 2. The only thing that changes during the compression, stiffness doesn't change of the spring, so only the compression amount is the thing that changes here. So I can actually write this change as k over 2 x final squared minus x initial squared. And if I look at my diagram to determine what these things are right now, I see that in the beginning, I had 0 compression. And at the end, I have compressed myself right now by an amount delta x. Perfect. Which means here, my answer is going to be k over 2 delta x squared. Delta x squared cannot be negative, so is k over 2, they're all positive. So I can drop the absolute values. And then combining my two observations, the work done onto the spring right now, would simply be positive k delta x squared over 2. That's it. Now, let's assume that we don't have any information about the compression amount, but we do have some information about an impacting object, say a box here that's coming in with velocity v1. It's going to compress the spring to a maximum where that box again is going to find itself with no velocity. how do I find the work done onto the spring yet again over here? Same logic. The force here imparted by the box onto the spring is directed leftwards, and it is also space dependent. The spring is moving to the left to get compressed. These things are parallel. So again, I deduce that the sign of my work done needs to be positive. Then for the size of the work done by the spring, or I should say onto the spring, for the size, I don't have the potential information anymore. I don't have the compression amount. I don't have the stiffness. But can't I argue right now that all of the kinetic energy of this imparting box just goes into the potential of that spring? And therefore, again, I could technically express the change in the spring potential as the change in the kinetic energy of the box? I sure can. This is the premise of energy conservation, after all. So I could go over here and express that same work done onto the spring as the change in the kinetic energy of the imparting box. Again, kinetic energy, we saw earlier how to open it up. We can factor outside the mass over 2 and just compare the final and the initial velocities here. What are they? In the beginning, I have a velocity v1. And in the end, I have no velocity. I'm at maximum compression. Therefore, I end up with something that looks like this, minus mv1 squared over 2. And the work of the absolute values right now would be to eliminate this negative sign, as every other constant here is supposed to be positive. So this doesn't need any absolute value right now. And it gives us the size of the work done by the spring. So when I combine it all together again, the work done onto the spring is positive mv1 squared over 2. Suppose you reverse this question, right? And you ask, what is the work done onto the box right now? What changes? Let's eliminate the work done, no pun intended, for the actual spring, and see now the perspective of the box. And we're going to do the same logic. You probably know what's going to happen though. So onto the box, the force that the spring is exerting on it is going in this direction, and it's space dependent. The displacement though of the box as it's moving and compressing the spring is in this direction. These two are anti-parallel, which gives me a sign for the work done onto the box right now. It gives me a sign negative. Okay, now what about the size of the work done onto the box? Well, again, this one is easy. We can just look at the velocity that this box was coming in right now, and at the velocity that it has at maximum compression. So as it's coming in, it has a velocity v1, and as it's maximally compressing the spring, no velocity. So the work done onto the box can be simply represented as the change in its kinetic energy state. So we write this again. It is exactly identical to before. In fact, we open it up exactly the same way, and the exact same variables take place right now onto the positions of VF and VI. So VF is 0, yet VI again is that V1 that we have up there. Giving you an overall, after you take the absolute value and eliminate the bars, mv1 squared over 2. So that's the size. And if we combine our findings, the work onto the box is negative mv1 squared over 2, which is exactly the opposite sign of what was the work done onto the spring. Makes sense, since energy is conserved in this process. Okay, so far so good. We have another example though that I would like to talk about, that talks about a general force F being applied on some object. So this is our last example that we're going to go through. Now, on this box right now, we apply a force F. The box is not moving. We are told that this box though, after the force F is applied, will move D over here. And obviously the position here, the shift of the position is to the right. So displacement vector is to the right now. Okay, so I take a look again at the force F and my displacement vector. They are parallel, which makes my sign yet again positive for, again, the work done by this force. Now, what about the size? Well, this one here is a non-conservative force, so we cannot express it in terms of a potential or a kinetic energy state because I don't have any information on the velocities, the end velocity, for example. But what I could do is I could apply the simple, again, if I want to find this work done, I can apply the simple dot product definition here of F dotted with delta D, which we've seen before opens up like this, F delta D cos phi. Now again, the cos phi here, again, we see that the force is parallel to the displacement. Therefore, this is an angle of 0 and the cosine vanishes. So really, what you have is F delta D. And we know that these are magnitudes. F and delta D right now are magnitudes. Therefore, I can drop the absolute values and write it like this. That's the size of my work done. The displacement, though, before I finish my answer, should be noted that it's given as D on the diagram. So that's what I will use right there. And my final answer for the size of the work done will be FD. Combining the results again over here, we see that the work done by F is simply F times D, and it is positive. So, what if you weren't given the displacement and you were actually given the velocities? What do you do now? Well, this is again still fairly straightforward. We see that the box has a tendency right now to move to the right, and it does move to the right. So the displacement again and the force are actually aligned, which makes the sign here that I'm expecting to be positive. But the size of the work done on the box, this time around, I don't have any information on the distance that the force is acting on. However, I have information on the kinetic state of the box. And I can use, again, the work energy theorem to claim that the work done right now on this box is going to be equivalent to the change in its kinetic energy state. So instead of F dot delta D, I use the kinetic energy information right now. So again, I open this up the same way that I've done before by factoring m over 2. I consider the final minus the initial velocity over here. And they're all squared. And I look at my diagram. The initial velocity is 0. The final one over here is v2. So I end up with absolute value of mv2 squared over 2. None of the quantities inside the absolute bars here is negative. Therefore, I can drop them. And then having the size right now of the work done onto m, I can combine it with a sign information to give a final answer, which is going to be this time mv2 squared over 2. And that is my answer. You can see that it differs very much so from the previous because, again, I'm given a different set of variables. I'm given velocities in this one versus the actual distance traveled in the previous one. But these are, again, equivalent descriptions, just seen from a different variable set. So that's all I wanted to actually talk about. You can do some examples of your own and try to determine the sign first of the work done by looking at your displacement vector versus your force vector that you're analyzing. So determine the sign, and then for the size, you might use the fact that a force is conservative and express it as a change in potential, some kind of potential. Express it as a change in a kinetic state. Or finally, if you have distance information, you can use the definition again of work with respect to displacement to do your actual size calculation. I hope you found this helpful. And now that this is explained, it causes a little less confusion on how to actually put those darn signs on the work done correctly. Thank you for watching, and I hope this helped.